Welcome to atoms bonding. So today we want to go over a whole bunch of things about atoms bonding and how they do this. The first thing that we have as a question is, how many valence electrons does chlorine have? And the answer is 7. So we want to get into today exactly how do we do that and what's going on with those different elements and how they're, how we're bonding them together. So valence electrons, if you remember, at the top of the periodic table, they have usually numbers at the very top of it. Usually they're put in there with Roman numerals, and those Roman numerals are there so they're kind of like a designator saying, okay, these are how many valence electrons each of the elements have. Remember, if there's a letter like A or B, don't worry about that at all. That's not what we're worried about right now. We're just worried about Roman numeral 1, 2, 3, 4, 5, 6, 7, or 8. 8's going to be the maximum number that they have at the top of those groups on the periodic table. Right? In chlorine's case, look, chlorine is over here in group 18 on the periodic table. And if you look at the top of it, it has the Roman numeral 7 right there, like we talked about in class. So that means all of these elements in this particular group, they all have 7 valence electrons to them. So what we're talking today is about atoms bonding together, how they chemically bond together. And this is the force that holds atoms together. So whenever you see some kind of chemical compound, say H2O, which, by the way, that's a chemical right there. So the next time someone tells you stop eating all those terrible chemicals, they're horrible for you, that's not exactly true. Water is a great example of a chemical, more than one atom or different types of atoms held together. That's a chemical by definition right there. In fact, if you want to have something that's not a chemical, really the only way to have matter that's not a chemical is if you have just pure, one of the elements. It's just pure, say, titanium right here. But chemical bonds are the force that hold those atoms together, right? So in our case right here, we have the one big oxygen in the picture and 2 little hydrogens, and they're being held together, right, by that chemical bond. Not to be confused with James Bond, obviously. Now, once you have this chemical bond, once they have chemically bonded together, you can't separate them apart by any physical means. And a great example of that is rust, right? Rust is just the metal combining with oxygen that's in the environment around it. That rust, you can't get it back. There's no chemical thing that you can do. There's no physical thing you can do to actually get the rust back, or well, get the metal back that's turned into rust, right? It's literally combined into a new material. That means there's no physical way that you can get it back the way that it used to be. Now, there are many chemical reactions to talk about. Unfortunately, there are a whole bunch that I can't do here in the classroom, especially this year is kind of crazy. But let me show you this short little video that does show you some really interesting chemical reactions. Now, here is one that we did do the first day of school, if you remember, where the dollar bill catches completely on fire. But look, it's totally fine. Here's another one that is very common to see right here, elephant toothpaste. Often they do this in college, maybe outside in some cases, because the gas that comes off of it is not very good for you, and it does make a big mess. But it's a really great experiment that's going on there. He's showing you it gets really, really hot. Right? We'll get to exothermic reactions a little bit later. But yeah, this one makes a mess. This next experiment right here is interesting because it's a liquid, but when you pour it out, look, it turns into a solid. Right? In fact, it didn't even make it out of the flask. He was pouring it so fast. That is a chemical reaction right there. This is one like we did in class. We did the much safer version where we just sprayed a little bit of the chemical onto fire. But you can actually have larger sections of the chemical, of the elements, and burn them. Here's another experiment here where he's mixing 2 things together. This one, unfortunately, makes a highly poisonous gas, which is why everyone's kind of laughing about it. But what he's doing is he's capturing the gas inside that big tube. And the fun thing is, once you have that tube and it's full of all the gas,
what I'm going to do is take the stopper off.
Well, you can light it on fire, of course. Oh, I can't believe they won't let me do that in class. The nerve of them. Here's another one very similar to that one, full of gas and some fine particles. Here's the birthday cake one right here. It starts off with, well, a bunch of pieces of what appear to be foam. It's chemical. He lights it on fire. And why won't they let me do this one in the classroom? I just can't understand why they won't let me do this. It seems pretty simple and benign. Well, but then the chemical reaction happens. Oh, yeah. This one, even in a college setting, I can't believe that they let them do it. It seems like this is just asking for trouble right here. This one's going to set off the fire alarm if he opens the door. So those are some great examples of chemical reactions, right? And there are a whole bunch more if you look them up and everything. Which brings us to the chemistry joke. There are many chemistry jokes that we could talk about, but some of them just don't get a very good reaction. All right, anyway. Hey, so we are in chapter number 2, right? Now, if you remember, we did chapter 1 in chemistry, which was what I like to call the ABCs. We were learning like Ne for neon, C for carbon, that kind of thing. That's like way back in kindergarten when you were learning your ABCs. Now, this chapter, the second of 3, the middle chapter, is kind of like when you get in a little bit older into elementary school and you start learning, well, things like how to put those letters together, right? So, in our case, maybe, putting carbon and titanium and phosphorus together, for example, right? So that's chemical bonding. That's where they're bonding together. There is one other chapter that we'll get to in a couple weeks here. And in that last chapter, kind of like the end of elementary school, is where you're learning to take those letters, put them into words, and now combine them into sentences. And that's what we'll do with the third chemistry chapter. We'll take, first those element symbols. We're going to group them together into kind of like words, but chemical formulas. And then we're going to make them into sentences where stuff is happening with those different words in it. So again, that's why you needed to learn, some of the element symbols on the periodic table, because you're going to need them. It's kind of like knowing the alphabet when you're using that. So when we're doing this, when we're talking about atoms bonding together and everything, we need to talk about some different things that are happening with those element formula or those chemical formulas for it. So that brings us to the spooky basement numbers, right? If you look at chemical formulas like our good friend H2O right here, well, look, the 2 is kind of like dangling down below here. What in the world is up with that 2? Now, that's called a subscript. And whenever there's a subscript, it's bonded to whatever element symbol is right before it. So in this case, the 2 has to do with the H right here, but it has nothing to do with the O or anything before the H. It's just, the subscript is just telling us the number right before it that's connected to. And it's just saying how many of whatever that element that is. So in this case, for H2O, it's telling you in the formula for water, there are 2 hydrogens and 1 oxygen. So if there's no subscript, it's just assumed there's just one of them there. But if you were making some other formula, you could have H5O or H355O or something like that, right? So the subscript are those little numbers that are kind of dangling a little bit lower. It's not a typo or a mistake. It's just telling you how many elements there are for the one right before it. So you've got your subscript number right here, and you've got the element symbols. So we've kind of moved on a little bit and everything. The other number, though, that pops up in these chemical formulas are called the coefficients. The coefficient is a number that's before whatever the molecule is, right? And so it's very different. The coefficient, it's a full size number, just like you'd be used to and everything. And unlike the subscript, which is just connected to the one element symbol right before it, the coefficient is connected to the entire molecule, right? The entire chemical compound that is, right there with it, right? In fact, if like this says 3H2O, if there were more symbols, let's say there was titanium and potassium and things after it, it would be connected to all those. It keeps going like that. The only time it's not connected to the element symbols is if there's a space. So if there's a space here, and then after this a little bit later, there's like another element or chemical formula, then, this coefficient's not connected to it. But all that it's doing is it's telling you how many H2O molecules you have. So it's like saying, there are 3 H2O molecules. So it's to save you work again, right? Instead of having to write H2O, 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 you just put a 3 right in front of it, right? So the coefficients, they're the entire molecule. The subscript, just the one particular element that it's connected to, right? Oh, so there you go. Here's my picture. This is kind of like saying 1 H2O, 2 H2Os, 3 H2Os right there. The elements have to form in a very specific ratio too, right? So H2O has got to be H2O. You can't have H2, and I don't know, you can't have like HO or something like that. It's got to be very, very specific for us here. Oh yeah, we got that. So let's do this, right? Let's give an example for H2O, right? What if we make a fortune? We're going to make a fortune on this, right? Because we're not going to spend a lot of money. We can charge whatever we want. People are going to buy it. We'll be all super mega rich very soon, right? What we're going to do is we'll market new water. Oh yes, old water was amazing, but new water is even better, because what we'll do is we'll take water, H2O, and let's just change it chemically, just a tiny, tiny little bit, and it'll be amazing, right? So all we'll say for water is we'll add in 1 extra oxygen atom, right? Well, what harm could that do? Oxygen, it's a little part of the air that we breathe. Everyone seems to think oxygen's really good for us and everything. So by taking H2O and adding an extra oxygen in there, that'll be a great deal, right? But here's where the specific ratio matters tremendously in chemistry, right? Tiny, tiny little changes can have humongous impacts that, well, you might not even know about and everything. Because while H2O is water, it's refreshing. Without it, in a few days, you would die. H2O2, turns out that's the formula for hydrogen peroxide. And if you drink hydrogen peroxide in enough volume, well, it's poisonous. You're going to die, right? So you would think just by adding 1 extra atom wouldn't change it very much, but it can change it dramatically, all right? So you can have huge impacts just by changing 1 little tiny element in a chemical formula for it. Right, let's do this, for example. Helium, you guys are all familiar with helium, right? Think about the Macy's Day Parade and the big floats or, blimps and things like that are floating because they're filled with helium. It's very, very non-reactive as far as the elements go. But its good friend hydrogen, right? Hydrogen right here with just 1 H, just a tiny little change, just 1 element away. Well, have you ever seen this video of what happens if there's a whole bunch of hydrogen? Here is the Hindenburg blimp coming in for a landing in New Jersey a long, long time ago.
And you are about to see the pictures he got when the ship exploded. Those aboard leaping for life from a flaming
Unlike
inferno.
modern blimps, this one was filled up with hydrogen. Modern ones are filled up with helium. But here's what happens. 1 little spark in the tail of the ship, and the entire thing just explodes in a matter of seconds. It burns. This is what happens if you use hydrogen, which is super, super reactive, compared to helium, which is non-reactive.
Rushing to the rescue.
All right, so tiny changes in chemistry make big differences in everything. How about this? If that wasn't shocking enough for you, how about this? If we take hydrogen, which we just covered right there and everything, you combined it with oxygen, which is also super, super flammable, highly reactive and everything. But think about it. You combine the two of them together, hydrogen and oxygen, both super flammable, and you get water. What in the world does that make sense with, right? Think about it. If something's on fire, let's say over here, what are you going to throw on it? More hydrogen and more oxygen, 2 of the most flammable things that we know of. Well, that makes no sense at all. But that's kind of the beauty of chemistry, right? This is why there are only 92 elements. There's only 92 ingredients on the entire periodic table naturally occurring, but you can make up everything in the entire universe from those 92 elements, right? And because just 1 little tiny atom in a chemical formula can completely change the way the entire thing works. Right? How about this, right? For an example, right? Sodium, super explosive. Remember, we talked about it. If you have sodium, you put water on it, it just blows up. I mean, that's just crazy. Chlorine, super, super poisonous, but you put them together, that's the formula for salts right there, which, we all use every day. Right? That comes to the lyric, right? Little Janet was a chemist, little Janet was no more. What she thought was H2O was really H2SO4, which is sulfuric acid, right? Again, hydrogen and oxygen, right? But you change it around a little bit, and it changes completely what the thing was. So atoms and bonding, right? Basically, when atoms are bonding together, right, chemically bonding together, we're forming some kind of new substance called a compound. Once it does this, it's impossible for us to pull it apart or separate it by some kind of physical means, right? When you're writing these out, it's in a very, very specific ratio, right? You cannot mess around with that. It's either right or wrong to get the exact thing that you want. And when you do this, when you combine atoms together, right, they chemically can be completely different. Like think hydrogen and oxygen, very flammable. They come together in the right ratio, make water, which you use to put fires out, right? And then we talked about the different things, right? There are the element symbols that we did last chapter. Now we're learning about the subscripts and the coefficients, right? And when you're doing it, like I said, you never use number one, right? If there's, if you have like one oxygen, you just put the O there. You don't need that subscript, to show it and everything. So let's practice doing some of these. Normally we do this in class, but you can just grab a piece of paper at home and work on this and everything and write down the chemical formula. So if I tell you water, right, write the chemical formula for water down. Here's my little picture of an actual photograph of a water molecule. Well, this is actually a couple water molecules, but you can see right here, here's the oxygen atom and 2 hydrogen atoms for us, right? Ironically enough, while we've been able to take pictures of atoms for decades and decades now, taking pictures of complete molecules was much, much more difficult. That's a relatively new invention. It was much harder for scientists to focus on them than just the individual atoms. Anyway, water, right? 2 hydrogens, 1 oxygen. Hopefully by now you've written it down. H2O, right, is what you should have done for it. How about, I'll tell you, write down some carbon dioxide. And for this one, we're telling you, there's carbon in there and there are 2 oxygens, right? So for carbon dioxide, right, the stuff we breathe out, plants breathe in, you should have CO2. Next one, how about laughing gas? Oh, and 17 laughing gas molecules, right, is what we're having you write down here. So in laughing gas, it's got for each one molecule 2 nitrogens and 1 oxygen, right? So for laughing gas, it's no laughing matter for laughing gas. What you should have written down by now is 17 N2O, right? So 2 nitrogens, 1 oxygen, and we're asking for 17 of those molecules right there. How about this one, whiteout, right? If you like to paint with white paint, it's got some titanium in there. And whiteout basically is just white paint in a small little container. There's not really a whole lot of difference for that. They just try to use a type of paint that dries really fast. Anyway, the formula for this is just titanium and 2 oxygens. So you should write down TiO2. Next one, 41 molecules of plaster of Paris. Right, so 41 plaster of Paris is used to, make volcanoes and piñatas and things like that. So you're going to write down 41 calcium, Ca, sulfur, right, and 4 oxygen. So O4 is that. Saltpeter, right? If you want to make some saltpeter, the main ingredient of gunpowder, well, here you go. You need to have this one right here, potassium, nitrogen, and 3 oxygens for saltpeter. If you want to make eight molecules of table sugar is what they're asking for us. So we've got some sugar coming through right here. Right? What you need is 8 of them, and then C12, H22, O11. Whew, okay. There must be some kind of problem with the smell in the room because they want 117 antiperspirants. So for this one, you need to write 117 aluminum. There are 2 aluminums, 1 chlorine, 5 oxygens, and 5 hydrogens for that. Right? How about 3 NutraSweets? Right? So if you want some NutraSweet, here's the formula for it. They want 3 NutraSweets, so 3 of them. 14 carbons, 18 hydrogens, 2 nitrogens, and 5 oxygens. Oh yeah, the element of confusion right here. Hopefully is not taking over for you and everything. Okay, then the other thing to talk about are the dot diagrams, right? The dot diagrams are worried about those valence electrons again, right? So how many electrons are in the outermost ring, if you remember that we were talking about, of whatever the element is. So how about this one right here? We're talking about some krypton right here and everything. Krypton is right here at the very edge of the periodic table, right? If you look above it, it's got 8, right? Roman numeral 8, so that means it's got 8 valence electrons. There you go. And to actually do the electron dot diagram, right? All you're doing is putting the element symbol in there, and then you're putting the number of valence electrons around it, right? And for now, 2 is the maximum we can have on any one side. And for us, we're not worried about it all, like where those little dots go. I'm not worried about that at all. That could be later in chemistry, maybe in high school or something, to learn about that. but that you have the right number of them is what matters. Since 8 is the maximum number they have, 2 on top, 2 on the left and the right, and 2 on the bottom for it. The next one to practice is nitrogen, right? So find nitrogen on the periodic table. It's right there. If you look above it, it has a Roman numeral of 5. So to actually make that element symbol, or well, the electron dot diagram for it, also called the Lewis dot diagram, right? Well, nitrogen, and you have 1, 2, 3, 4, 5. And again, where they go is totally up to you. You can put those 5 dots anywhere that you like for it. The next element, zinc, right? We've got some zinc right here on the periodic table, right? Valence electron number is 2 right above it, so it has 2 electrons. And then for zinc, put those 2 dots wherever it is that you like for it. Last one, francium. Okay, scary francium on the periodic table. It's way in the far bottom corner over there on the left. Hopefully you know what that means. You do not want to mess around with some francium, that's for sure. It would be very dangerous. It has 1 valence electron, which is why it's so dangerous and everything. So to make the electron dot diagram for francium, put francium symbol right there, put a little dot beside it, and you're good to go.